Hi everyone, and welcome to the first SPM Python lecture. So I'm Johan Medrano. I'm a postdoc fellow at MIT, and I was previously a postdoc fellow at the Phil, and I'm now honorary research fellow there. So it's really nice to be back and get to see all of the previous coworkers. So today I'm going to be talking about this new Python wrapper that we developed for SPM. And I'll go into a bit of how it works and how it's been constructed, and we'll have a bit of a show and tell, and we'll finish on a Q&A. So Okay, let me just. Yes. So today's program, I'll just first explain how it works. Then I'll explain very quickly the requirements and installation. Then we'll have hands-on. So I'll show a few Jupyter notebook just to show how to work with the type system, basically how the basic of SPM Python works, and how can we work with MNE Python. Then I'll just explain very briefly what to do if you want to use SPM Python, need help, support, or want to get involved, because well, yeah, you can get involved if you want. And then the future directions for the project, and then we'll have a Q&A where you can ask all of the questions that you want. So just if you well, yeah, I'm just going to get started. But before getting started, I just want to thank people that have gotten really involved in the project, especially Yael, Yulia, Arthur, and Suvadip, who yeah met regularly uh, and did like a lot of the work to make this project happening, and also Olivia, Peter, Tim, and the SPM development team in general. I think there was a lot of excitement behind this project, and I think these are the people to thank. How does SPM Python work? So basically, MATLAB provides us with something called MATLAB compiler that allows us to take a project that is fully written in MATLAB, like SPM, and then wrap it into a Python package. The only problem is that it's a bit hard to understand how to interface with this Python package, because MATLAB doesn't expose most of the functions that are in the package. So you kind of like have to try and guess what you can call on the package, and it's not convenient to work with. So what we wanted to do is to make it actually. So this is functional, supports like a few a few like original MATLAB types, but it's not functional to the point that we like. For instance, you cannot do like multidimensional cell arrays, which are quite useful. It means like you cannot load in Python like a SPM.mat, for instance. So this is it's a good way to start, but it's not it's not sufficient. So what we've done is to develop a package that generates automatically from SPM code a user-friendly interface to the Python package that is generated by MATLAB, which means that now you can have an interaction with the package, which is much more natural or much more similar to the one that you would have in if you were working directly with Python code. So we wanted to have like a more Pythonic, yeah, interaction. And so this is what this MPython package is doing. It's generating the user-friendly interface. And so just when we talk about SPM Python is indeed all of this full pipeline here. So it's yeah, all of this. And what does it mean? It means that SPM Python is not a reimplementation of SPM, and it's not different from SPM. It means that running code from SPM Python is actually calling the underlying MATLAB routines, which means that the code is the same and the results should be the same. And that's mostly due to the fact that MATLAB has implemented some really nice thing in the code that they use to generate the Python package, which allow MATLAB and Python to share memory. So normally, like even to the floating point precision, things should be the same. And on what we've tried so far, it's mostly, yeah, it's very consistent. And so if you know to use SPM in MATLAB, then you know to use SPM in Python if you know a bit of Python. And all of the things that you've learned about SPM this week, uh, well, you can also do them in Python. So I'll just show you or explain you very quickly how to what are the requirements for SPM Python and how to install it. And so there is three steps. The first one is to install the MATLAB runtime. So this is like it's a little program that is packaged by and distributed by MATLAB that allows you to run uh, packages like SPM Python that are constructed around MATLAB, but without having a MATLAB license, which makes it as accessible even if you don't have a MATLAB license. Then you need to install Python, obviously, and then you install SPM Python. To install MATLAB runtime, I'll just explain very quickly. If you have a MATLAB license and MATLAB 2024B, then you can install the MATLAB compiler SDK through the MATLAB interface. So it's really simple. You open MATLAB, you go to the tab that says apps, click on get more apps, type MATLAB compiler, and you'll find this package. You just click install, and that's going to be it. If you don't have MATLAB, then what you can do is just to click on this link or go to just type MATLAB runtime um, on Google, and you'll be redirected to this website. And here you'll choose the release R2024B for whichever platform you're using. And it might be a lot of, and for simplicity, use the default installation path. And it might be a lot to remember. So if you go to the SPM Python GitHub repository, which is where the code lives, um, if you go to the wiki, you will have an installation guide that basically tells you all of the steps to do with, yeah, you've got links to installing Python 3.12 and the latest well, MATLAB 2024B. And you should have like a bit more instructions there. Second step is to install Python. So you'll need a version of Python between 3.9 and 3.12. And you cannot install the Microsoft Store Python. So don't go to Microsoft Store, click on install Python because that won't work for some reason. I think it's not compatible with what MATLAB expects. So yeah, so you have to download it uh, from the official release or from Anaconda or something like this. And if you're not sure, just download it from the official Python website. And the next thing to do is to open a terminal. So in Windows, a command prompt, and just use pip, which is the package manager for Python, to install in SPM Python, which gives something like pip install SPM Python. And then to test your installation, you open a Python console and you type on Windows and Linux, you type just Python. On Mac, you have to type MW Python, and that's a bit something different is that MATLAB runtime, for some reason, the Python version of MATLAB runtime doesn't work with the default Python and Mac. You have to use the version of Python that they package, which is called MW Python. And then you can just import SPM and launch the GUI, which is, I think, something quite interesting. So I'll just show you very quickly. I've got a command prompt here. I'll create a new command prompt. And here what I'm going to do is just open a little Python terminal, import SPM. And then I'll just start the normal GUI. So here it will initialize MATLAB runtime. That can take a bit of time. the thing is that you will have like a bit of a overhead at the beginning when you start using function in SPM that requires MATLAB, and then running it is actually quite fast. And then the nice thing is that you actually have your SPM here, uh, and it's exactly the same as in MATLAB. So you can launch the MEG interface and do all of the things that you would usually do. And notice that these are actually MATLAB figures. So yeah, but it's the normal SPM just there. Okay. So now I'll explain a bit more on the ways of SPM-Python and how it works and what things we have tried to develop. So the first thing is the type system. I'll just explain quickly how the type conversion work, and then I'll run a little notebook that you can find online as well. I would suggest uh, not to run along for now, but to go back to it, download it, and run it in your own time to get a grasp of everything. And I think it would be also more interesting if you can try to play with this object and see, yeah, whether it makes sense. Um, so the general rules are that MATLAB objects such as like cell struct array and normal numeric arrays are just translated into the same thing in Python. So a cell is a SPM.cell, a struct array is a SPM.struct, an array, numeric array is a numpy array, but it can also be SPM.array. So you can choose whichever you prefer. And for instance, translation of MATLAB code into Python code gives something like A equals cell of, to create a cell with 3 colon and 1 row, you'll just type spm.cell with 1 row, 3 colon. Then to create a cell from a list of, for instance, region names, here you would use spm.cell.from any. That just says like, well, it will just try to look at what you pass to this function and interpret it and generate the cell for you. Then C equals struct will be C equal SPM.struct. Then affecting to a field of that struct C.A equal A will be the same thing. And then C.array equals this 2 by 2 matrix will just be the same thing, but with a numpy array with the correct number of dimensions. And so now I'll just show you what it means in Jupyter Notebook. So I just started a new Jupyter Notebook. I'll import SPM. And okay, I'll just go back a little bit before getting into the type system. I think it's important to know how to get help very quickly when you're developing. And something which is quite nice is that we kind of constructed the wrapped code in Python such that all of the doc strings that are associated with a function or class are actually containing the thing that you would get when you call help in MATLAB, which means that now if you call help, for instance, on this SPM DCM ERP, which is something that uh, well, if you do DCM, you will often use help on this function. Then you'll see that it will just return all of the help that you would have had on this function. So what arguments does it expect, and what field in this structure does it expect, and then if you want to have a look at the SPM at the MATLAB code, you can just click on this, and it will redirect you to the latest version of the code in MATLAB, so that yeah, you can also read the code. And I think it's been said before, but SPM code has been made to be quite readable and quite didactic. So you can go ahead and read the MATLAB code. Sometimes it can give you a good intuition of what a function is doing. It works for class as well. So you can get more info on the class itself. So for instance, the MEG object that contains a MEG or EEG data set. And here, if you do help on a full class, what it will do is list everything in that class. So that means the init function, but also all of the methods that you can call on it. So it can be very useful, but it can be also a lot of information. If you just want to get information on how to construct the object, you can just call help on the init, which is the constructor of the class. And here you will have like all of the accepted way of constructing an object. And you'll see here that the argument list is actually flexible. So this is like anything that is not a keyword, well, or dictionary-based arguments. And this is all of the things that are yeah, name value arguments, and they will just be taken and passed to MATLAB. So you can use all of these syntaxes without too much thinking about it. And what it will return to you is exactly a MEG object. So now going back to our MATLAB-like types. So we said that we had three different types, SPM, well, three different base types, cell, struct, and array. So cell arrays are quite simple. You can construct, like for instance, a cell of size 3, then populate the cell array with data, and then you can print the cell array. And you can do something that is not common in Python, which is add a new element in an undefined index that you see, which is a syntax you can do in MATLAB but not in Python, and that will update the cell array. So if I run this, you can see here that I've got my 3-element cell array, and then I index the 5th element, so index 4, because indexing starts at 0 in Python. And now I've got my updated cell array. So here I have well, I have this MATLAB syntax, which will allow us to, for instance, write MATLAB batches and things like this without thinking about constructing like all of the fields of the structure array beforehand. We then have like a struct type, which is, well, straightforward struct, which is basically working like a dictionary in Python, but with dot notation to access the fields. Well, you can use either the dot notation or the square bracket notation, both would work. And then you can construct struct array that have different shape. So here it's 1 by 3 array. So we adopted MATLAB convention just to make it more straightforward for people coming from MATLAB. Basically, if you put a single dimension, then it will assume that that it is a column vector, which is the opposite, I guess, to what is naturally done in Python. Then you can create like a 2 by 2 array, and you can also affect like a new field to an array, but this is similar to a dict. And so here, if I look, I've got single struct, a struct array, one-dimensional with 3 elements, and then a 2 by 2 structure. And then I've updated my first structure with a new field. And then the last class is the normal, is the kind of generic SPM.array, which is just a NumPy array with a bit more like functionalities, but and well, different functionalities, and basically it would work as you would expect. So you can create arrays of different shapes. And so one of the very important thing and very like a neat thing about these classes is that, well, Yale spent a lot of time to make all of this work, but deriving all of the class from np.ndArray. So it's not, yeah. So they've got kind of the same functionality as you would expect from object that you would work with in NumPy, which means that, for instance, if I create a one-dimensional array, fill the array with data, and then I reshape it. I can reshape it to like whichever shape I want, and I can also like transpose it, which means that, yeah, I can do all of my very natural operation, and that just allows you to do array operation on more like non-trivial data types, as you would do in MATLAB, and that will just help you write, like being more succinct in writing code to pass to SPM. Um, so same thing for, well, we can also concatenate structures, which is quite useful. For instance, if you want to concatenate scans or data sets or things like this, you can just use the np.concatenate. And then we can do the same thing naturally with cell arrays. And the last thing that is a nice and useful, I guess the most useful and the most, well, that is the feature that motivated us to write this type system, is the type inference as construction time, which means that if you do like some indexing sequence, so in MATLAB you can write, you can create some empty object and then do like a very long indexing on it with different cell type or array type or field or structure type indexing, and put a value there, and MATLAB will automatically infer what all of these nested objects should be and where should the data go. And we've managed to reproduce this in Python, which means that, for instance, you can create an empty spm.struct. And then if I want to create a struct array with a field that contains a cell array with in third position, a struct array, which is a 2 by 2 random matrix that is stored in the fifth position of the struct array, then I can, oh, actually, this is not correct. The indices should be -1. But apart from this, it will just infer all of the things that you need to put. So for people that have already used the MATLAB batch, well, you probably have seen that MATLAB batch has a lot of indexing like this. And so this kind of notation allows us to work more conveniently with the MATLAB batch. And just one little note on this is that naturally, if you try to do this notation where you construct, for instance, a struct, index it field, and then you want to assign something in the using cell indexing in position 4 and put like a value like test, you will have a problem here because so the round in brackets they reproduce the behavior of the curly brackets. But the problem is that round brackets are indeed function calls and you cannot affect them, so you will have a syntax error. So that's why we constructed an additional rule. So the additional rule is just you can use as cell to affect something um, in an object and specify it as a cell. So if I run this will be a structure array with one field called fields, and its value is a cell array. And in the fourth position of the cell array, we will have something written test. And so this array, this is now working. And just to remind you the rules of type inference. So these are just applying whenever you want to construct an object very conveniently or very like quickly, using like a one-liner like this. And the rules are dots to create new fields, square brackets for array indexing. So that will be indexing either numeric arrays or structure array, and round bracket whenever you would use this curly bracket in MATLAB, which would be cell indexing. So for things that have, for instance, different types. And the fourth rule is just use as cell to to construct a cell and when the assignment is within a cell. So that's it for the MATLAB types. And now we can see how to actually use them. So I'll go through two examples. The first tutorial is one that you probably have seen uh, from the website. So if I go to the SPM documentation and I go to tutorials, what the tutorial we're going to do is this one, the sensor level evoked response pipeline, which is basically showing you how to do preprocessing in SPM. And so we'll do exactly this tutorial, but in Python. So if you want uh, to look at it, to run it, you can go to the SPM-Python GitHub. So that's in the SPM organization, the SPM-Python repository. And then you will have like an example, um, you will have like an example folder. And in this, you will find like all of the different examples. And here we'll look at the sensor level evoked response. And well, I think this is out of the code. For some reason, it's been committed with a runtime error here, but it is working. And I'm just gonna run it. So this example will require you to download the tutorial data and to unzip it. Um, and yes, so I have already downloaded the data beforehand. If not, when you run the tutorial, you can just click on the link and download it. And then here, the purpose of this example is just to show you how to move from some MATLAB code that you might have to the equivalent Python code. And you'll see it's not so many changes. So here is the MATLAB code that we have for the first line, which is just creating a OPM data set. And so here we'll have just an empty structure, and then we've got the data and the positions that we put in there. And you'll see that in SPM, we do exactly the same thing. And we construct a SPM struct. Then we affect the path for the data, the path for the positions, and then we just call SPM OPM create. Note that I've used the star import here. I don't think it's a good practice. It would be better to just do import SPM and then call explicitly spm.struct and spm.opm create. And so here, this is the thing you will always see, which is initializing MATLAB runtime, and then it's just gonna run the underlying code. Okay, so now it's run this. And now what I can do is to look at the object that has been created. So this is the object. And here I can see that it's a spm.meg.meg object. So I think I can do this if I wanted to see, oh, wow. If I wanted to see what it is, well, I've got the help here about my object like as before. And now you'll see that if I try to use one of these methods, for instance, I don't know, Chan labels, I can just, so type dot, start typing the name of my method, type it on tab, and then I've got the auto completion that shows me Chan labels. And so that is a function. So I'll just call it. And here, all of the labels returned as a cell array. And so, yeah, all of the natural functions that you will have on the G object, you can just call them here. So now we'll take our D object and we'll compute its power spectral density. And so here is the MATLAB code. If you were to basically transfer it into Python, what you do is quite simple. So Python can read the semicolon. You can remove them if you want. But basically, I can show you. You just do this. Then you replace the empty struct by struct. And that's it. You've used your MATLAB code into Python. Uh, and so here, I think it opened. So that's one of the kind of weird thing, or let's say a bit unsettling thing, is that all of the plots that you will construct in MATLAB will be, well, in a MATLAB function. So for instance, SPM-OPM PSBT that has this option to plot the power spectral density, it will create a MATLAB figure. And that's a bit unconventional and not so practical, just because, well, everything stays in MATLAB and it's not converted to Matplotlib. This is kind of out of our hand for now. So what we are trying to do is to make it more easy to edit like the labels, the axis, and all of these things. On the other hand, because of the underlying like renderer that MATLAB uses, it's not straightforward to integrate with Matplotlib. We hope that uh, that MATLAB will provide us with options there, but I'm not sure of how that would work. So for now, we will have to stick with that. So two options there. One, do your figures with MATLAB. Second one, get the data into Python and use Matplotlib or Seaborn or whichever favorite library you have. And then I'll just move a bit more quickly because this tutorial, I think you got the gist. We always take the MATLAB code and then replace anti-struct with anti-struct and then just run the Python code. And here we'll see, I think, one variant. So here we've got this code that is, so here we've done the preprocessing of the data set. And here we've got this part of the code that is supposed to, same as before, compute the power spectral density and show us the power spectral density for after preprocessing. And so the problem is that well, one of the things is that here you'll see that it's returning the frequency array for use with other. I think it's used to customize the plot, but we don't do it here. But I think here one of the important subtlety is that this notation is not a valid Python notation. You cannot just unpack things like this. And also under the hood, when you do this, MATLAB kind of reads this full expression and then determines how many number of output arguments it should prepare for you. And so when you're passing code from Python, you cannot really do that. MATLAB cannot access the Python code, read it, and assess how many return arguments you want to have. And so instead, what you need to do is to call the function for which you want to have many return arguments with an arg out, which will just say to MATLAB, oh, I want you to fill in two output arguments. And then the equivalent of this tilde notation, which basically says, I'm not going to use this argument, and is usually the underscore notation in Python. So that's it. Yeah, subtlety here, just use an argout whenever you want to have several output arguments. And yeah, this was. And then we can do epoching and baseline correction, averaging, and plotting the data in the same way as we will do in MATLAB. So that's it for this tutorial. And I think the last thing I wanted to show is this last tutorial that you can also find in the same place online. So this one should have been run with all of the correct, yes, with all of the correct cell, it's been committed with all of the correct cell output. So if you just go to the SPM-Python repository and you go to examples and you click to MNE to SPM to MNE.ipython notebook, you will be able to just look at it and you'll see, without having to run the code, you will see what the code will generate, which is a nice feature of Jupyter notebooks. Yes, and this is the image that has been generated by the evoked response from the previous example. And you'll see that minus the plot configuration, it looks the same as we had before in the MATLAB version. So now I'll just stop this one. And we'll look at MNE2 and SPM interoperability. And this is an example that has been constructed by Julia, and she also made the helpers function that are under the hood and that allow you to take a raw object from MNE, take it into SPM, take it back to MNE, and play along with that. So I think it's a really nice thing, and I think it enables, well, it will enable us to work with both SPM and MNE if you want. So for this, to run this tutorial, you will need to, and if you have questions on this, I can see that Julia is here. So during the Q&A, you can just ask her. So for this tutorial, we'll need MNE and well, SPM-Python. Just quick note, pip install MNE installs MNE, pip install -u SPM-Python is installing or upgrading SPM-Python to the latest version. I would recommend to do that because, well, SPM-Python is under development. So for now, we're in the beta. We're waiting for MATLAB 2025 to be released. It's been released on, I think, Saturday or Friday. And now we need to do the final work to have it work with this, with 2025 and then we'll release. And that will come with a lot of new features I'll explain later on. So I'll just run this, but I think it should be okay on my computer. Yes, everything is fine. Then we'll import some useful package that we need, such as matplotlib, numpy, MNE, and set up the interactive mode on matplotlib to on. And then we'll import the SPM function. So from SPM, we'll need to import the AMM and struct. And we'll need the two functions that Julia has developed that are in spm.utils and that are SPM to MNE row and MNE row to SPM. So we'll just import this. And so that worked. Then we'll load the data into MNE, and then we'll just view what is there. And for this, we'll use the UCL OPM auditory data, but from MNE this time. And so this function in MNE is just helping us. Well, it will help us to download the data. So I've already downloaded it, so it won't download it again. But basically, we'll use one particular subject and session from this data set. And so here it will just load the data set and show to us what is in there. So we can see the sampling frequency. And so this is very, well, this is the way MNE display their data. So they are really well integrated as well with Jupyter Notebook, which is, I think, quite nice. I saw that yesterday. I think that didn't exist when I was using MNE. So a lot of development has been made there. It's really nice to see. So just here we'll just plot data into MNE. So this is more MNE related things. Just show what the data looks like without preprocessing. It's not so pretty. We can see a lot of artifacts there. And then just compute and plot the perspectral density here. You can see like a very sharp peak here at about 50 Hertz per line. Maybe like a bit of alpha here. And so now we'll do some preprocessing step in MNE. So remove all of the well, per line and harmonics here, and then apply a filter just to chop off our data between 1 Hertz and 70 Hertz. And all of this is done in MNE on the MEG channels. And then we'll mark some of the channels as bad. And then this is where the conversion function gets in play. Here we'll use MNE row to SPM. So just to show you, the object that we have now is actually a row object. So it contains, well, it's a MNE row object. And now we'll convert it to a D object, so a MEG dataset. And so here, once again, it needs to initialize MATLAB runtime, and then I'll just show you what data looks like. Oh, actually, don't need that. And here, out of this, we got a MEG dataset, which has been, which has been converted from MNE. And I think maybe Julia, you'll be able to tell us more about what kind of transformations are and are not accepted by this method.
Well, sorry, I think now it's only can use MNE row object, because the MNE has epoch object, evoke object, so it's the beginning, so it's only MNE row. I think there was some bit of a caveat about how it's translate gradiometers, but I mean the data is saved, everything is good. It's just annotation is a bit weird, but I'm working on it. Other than that, yeah, it's literally just creates the object, taking like information from the MNE row object and translating it to the object. That's it. Not a big magic there, but still cool.
Nice, thank you. And I think you also saved the transform matrix.
Oh yes.
As CSV files, yeah.
Yes. So I think it's on the other way around is important, because MATLAB has these TRA matrices that would save you, for example, from, so in OPM case, it will save you if you do some kind of pre-processing from the data, like the IM filter later, it will say you this transformation, what you did to the data, so you can then apply it to the forward model. So that's important to translate, and yeah, so this translates this TRA function, TRA matrix to the data, so it applies the projections right away. I can talk about it later if you have questions, because it's quite a not a clear in I'm not explaining it super clear, but yeah, but it saves the TRA matrix. That's important, so you don't lose this information.
Okay, nice. Then I'll thank you, Julia. I'll run the SPM to many row function, and we'll just look at the matrix that is created. Just yeah, I think something important here. You can give the path to the place where you want to save your new object, and I think in my case I just put it in the current directory, which is not so clean, but also yeah, it's easier to retrieve it later. And so I think if we go in that, we've got the SPM object that has been created here. And I guess it will create the transform object somewhere, unless, oh, it's not finished to run. Here we've got, so just to summarize, like this first step was we took the data from MNE, send it in SPM. In SPM, we applied MMM, and then we took the data from SPM, send it back to MNE. And here we've got the clean data, and you see the MNE format. And here we've got the row array, and we've got our bad channels that we've put before. I think some of them have been also annotated. And yes, and here we've got the projections that are constructed, and I guess
So I think if you save, if you already applied the projection, I think it doesn't save the matrix because it's
okay.
already applied. That's it. You can't
O-
unapply it.
Okay.
But if it can't save, for example, if it's CTF system, whereas um, matrix doesn't have the same meaning, then it just saves it in a separate file for you to deal with it.
Okay. Oh, I thought it was saved in all times. Okay, so here the projection will just be in the projection field in the raw object. Okay, cool. And then we can just visualize the effect of preprocessing here. And then we can do things that we would do usually with M&E, like epoching and then computing the evoked response and showing like these pretty plots that M&E has. And same thing for looking at the evoked response on the radial sensors and on the tangential sensor here. And so that's it. And I guess extension of this would be take like the data that you've got in M&E and apply whichever of M&E methods you want to apply to it. I know there is a lot of classification thing, a lot of statistical learning or machine learning methods that you can use. But I think it's nice to have a way to get the data from M&E/SPM, switch between the two, and then switch back. I think it's quite a useful feature, and that's how you do it. And you can, if you want to go again for this tutorial, you can find it on the SPM-Python repo in the example folder. And now I'll just go back to my slides. And we'll see how to get help and support and getting involved. So all of the code and related discussion are held on GitHub. And if you find so this is the link to the GitHub. If you find an issue, help us by reporting it. So you can open a new issue. So you will see this big button, just click on it and explain what problem you have. If you need help with something, also open an issue. It's very it would be very surprising that no one has the same issue as you. And the idea is that if everyone that needs help open an issue, then it means that the more issues have been open, once they not like people can go back to them and look through completed or closed issues and see what questions have already been answered. And you can also like refer people to similar questions. So that help us create some kind of documentation of frequently asked questions. And we aim to have as much discussion as possible on GitHub so that questions and issues are documented online. And that means like even if you've got suggestions or things that you think that would be a nice feature, you can open either an issue or a discussion on GitHub. And that would be the best way to get the ball rolling with this. And if you want to take part in the project or get involved, please reach out. For now, we have like bi-weekly Scrum meetings where everyone show and tell their what they've been working on. And if you want to join this or get involved by any way, just please reach out. You're more than welcome. And just to explain the future direction for this project, so it will be having a better documentation. So we're looking into how to integrate our documentation in the SPM docs, which is this very nice website that has the documentation for SPM and that Olivia has been putting on. And with Fano, we've got, I don't know if I will be able to find it easily. We've got another, yeah, I don't think I should have put the link. M-Python, which is the thing on which SPM is built for in terms of the base types, has also documentation that is listed online. So this is quite new, but you'll be able to get help on the base class. We need still to link it back to the SPM Python documentation. Then easier installation. That's something we have been like putting the most effort on, I think. And it's the idea is how do we make it, yeah, easy and straightforward for people from any platform, any type of MATLAB version to just install the package. I think it's quite nice when you can just do pip install of a package and oh, nice. Thank you, Julia. So here is MPython core is the thing that I was talking about that provides the base type for SPM. And so it has a website which, well, we still need to document. I don't, yeah, it is online, but I don't know why it's not showing up. I'll look into this. Anyway, there should be the documentation somewhere. And then better, so yes, easier into installation. The idea we've been working so that when, well, to kind of track or add the MATLAB runtime to pip so that when you do pip install SPM-Python, it actually installs everything you need. And yeah, we are getting closer to having that working. So hopefully that's gonna come soon. Better integration with Jupyter Notebook. So this is just to make everything more convenient. And then continuous integration. So the code I said earlier is generated automatically from the SPM code, but it's not yet automated. So it doesn't track all of the changes. We kind of do it manually. And so, yeah, the idea is to just have everything continuously mirroring the SPM repo and creating releases automatically. And so for now, SPM Python is in beta and will anticipate to release the first version or first non-beta or official version of SPM Python in June. So that's pretty exciting. And I think that's it. So I wanted to thank everyone that has gotten involved with the development of SPM Python. So Yael, Julia, Arthur, Suvadip. Thank you for the SPM course organizer for inviting us. I think it's really nice. So thank you, Alberto, Julia again, Vladimir, Peter. Thank you, the SPM team and the methods group and Phil in general, UCL for me, MIT, and Conda Forge because we are in the process of getting on Conda Forge. So that's really exciting.